Okay, having skipped ahead, I'm not going to go over the recursion theorem because we don't have that much time, and I'm not sure how much brain power you guys even have left. Because we've gone through a couple other things. The look on your face was like,
no,
it's zero.
I didn't sleep and I took the final, so I'm here now.
That's fair. So, okay, so, right. The halting problem proof is actually, I like this proof of it, it's pretty elegant. The recursion theorem is important, but the proof of the recursion theorem is not important. So let's simply talk about what the recursion theorem does. Because, okay, honestly, I think his note below the proof of the recursion theorem is really good, where he says that a computable function can know its own index. That's like the key.
Is that like the index number, like G?
Yes.
No, it's 2.
Yes.
Okay.
So like, yeah, that's exactly it. So essentially, in the computation of G, it can utilize the fact that it is the second index in your index. That's it. That's it. That's all it means. So does that make sense to people? It'll hopefully make a little more sense why we care about this once we do the halting problem.
So one of those G's knows it's E?
Yeah, all of the G's know it's E.
Okay.
Every G can know it's E. And you don't have to dig any deeper than that for the proof of the halting problem, at the very least. So let's go through that, because that's obviously going to be, I mean, it's a proof of non-computability. So I am almost positive, though I haven't done the proof myself yet, that 24.11 is not going to be doable if you don't understand the halting problem proof. So, okay. So, like all the best proofs by contradiction, we're going to assume that it is computable. Okay?
Mm-hmm.
What does that mean? What information does that assumption give us?
I was going to ask this. I wasn't sure, but is it maybe that we can define psi as follows, and like if it's blank if the thing's in halt, it's 0 if it's not in halt, like assuming that we'll always be able to determine if E's x/y is in halt.
You can always determine if something is in halt, so you're assuming it's computable, which means there exists a machine that decides it, right?
Mm-hmm.
So what your machine psi can do, this is a bit truncated, I would say, like his proof isn't specifically telling you what it's using at what times. Mm-hmm. But how you can build psi is, let's say you have your machine H that computes the halting problem. Well, just run it, and if it rejects, reject, right? Because if it outputs 0, output 0. If it's about to output 1, instead modify it to just loop forever.
Right.
Now you've got psi. So he doesn't explain why he can build psi, but that's why he can build it, right? Because he's assumed that there already exists this machine that decides halt. Does that make sense? No, cool. Okay, so things are like this. Let's start drawing things again. I like pictures. I better start a recording. Yep, good. Okay, so oh god, there's so many sides. Why are there so many sides?
I'm going to take a quick picture.
Does anyone want me to use something else other than psi for this machine? Because I kind of want to use, can I call this something else?
Gamma. And my gamma, just call it like a letter N.
Yeah. I'm going to call it D for don't halt, because this one doesn't halt when it halts. I don't know. Or is it... It's almost like... HALT inverse or something, right? It's like HALT bar. Can I call it like H bar? It's like basically like not, it's doing the opposite of whatever the machine it's simulating is doing. Okay, so we're going to try and define this H bar with, I'm going to use the same notation from earlier. I'm going to call the machine that decides the halting problem H. So, okay, we don't know that H bar exists, but we do know from our assumption that HALT is not, so HALT is not computable is what we're trying to prove. We assume the opposite, so we've assumed HALT is computable.
Right.
By definition of computability as in accordance with lecture 22, that means we have a machine that decides on any given input if the input is in the language or not in the language, right? That means we can build what they call psi-en, and I'm going to call H bar. We can build it by doing the following with H. If H of mx equals 0, actually, yeah, then H prime of mx equals 0, right? We can do this. We just and then if H of mx equals 1, loop, or IE. That's why I can say that this exists, is because I'm defining it based on something I've assumed to exist. Does that make sense? Pretty easy to just make a loop. You just like make it go back to the state, go back to itself at all times, and it does never accepts or rejects. So we just swap out one state. That's it. Okay. Well, we swap out any accept states, I guess. I don't remember if the definition of Turing machines you guys use has like, I think a set of accept states or something. Anyways, not a hard thing, but that's why he can build this psi. Let E be given, oh, and thank you for the laptop. Let E be, I need my glasses. I should be bringing them. Let E be given by the recursion theorem such that for all. Okay, so now he's going to apply the recursion theorem. He wants to utilize the fact that he's got E of n. So that's, so wait, how does he define the halting problem? Oh, he defines it right above. So it's an E and n. Okay, so he's going to, let's see. So presumably, so he's taking En, and then he's saying the function corresponding to the Eth index on the input n. Okay, so I have two choices at this point. I can continue with my notation and tell you how it maps to his, or I can use all the notation he's using. Which do you guys think would be easier, personally?
Well, we're probably going to have to meet his notation, right?
That's fair. Yeah, let's go with that. I agree. I always like machines. I think they're a little more intuitive than trying to map functions to functions. But let me at the very least always include his notation. So we'll leave that up for now, but I don't want to miss out on an opportunity to talk about indexed functions. Let's see. Okay, so his definition of HALT, let's put that up first, is, how are we doing on time? Not good. Good. HALT equals, we should digest this first. benefit of different notations sometimes is usually I know for myself at least, if I've heard something in multiple different notations, it sometimes helps me understand each of them better. Because I see like I can get too caught up in like a single way of defining something and miss like the intuitive meaning and structure of what's actually going on, and that's usually what you have to utilize for proofs anyways, if that makes sense. But yeah, we should definitely also use his notation. So the way he defines halt, what is this saying and why is this the same as what I said earlier? In the video I discussed halt. Well, what's this? Just the phi of e, phi sub e. What does that mean?
It's equivalent to the unary blah 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 that at all points.
This is the sum indexed unary function, and then for all e, this captures all functions.
Right.
You can think of a machine as a partial computable function. Is I think what like it's a is I guess what he's saying here, right?
Can you teach
And this is the input to the machine. But in this case, it's the input to the function. And so, like, when I say doesn't halt, he used doesn't converge because he's talking about functions, and I'm talking about machines.
So the down arrow means it does.
Yes.
Okay. So halt is the set of all those functions which do.
So halt is the set of all functions and inputs, such as on that input, the function converges.
So it's a set of e and n
Yes.
such that
The-
psi
The function
Phi,
associated with
whatever.
e, like indexed at e,
Okay.
essentially
given the input n halts.
converges.
So psi.
But yes.
Yeah.
So
Sorry,
phi.
converges.
No, it's fine.
Yeah, phi fixes the whole thing, right? Phi is what tells you what pairs are nice because the pair you take an e, you take that phi at that eth place,
Mhm.
and then you put the h in, and then you want it to converge.
Sorry, can you say that one more time?
It's a n. Yeah.
The n.
Oh, is that an n?
Yes.
Oh, I
Sorry.
see. Okay, okay.
Yeah.
I got you.
I was then confused with this h, and I was like, what's going on?
Right.
Okay.
So this whole set is kind of it's really determined by phi because you have your phi over here on the right hand side of the such that bar,
Mhm.
and then you take the eth input, and that tells you what like unary function
Yes.
phi is operating as, and then you take the n, and then if the n on that eth thing, which is simulating that weird psi from the first definition, if that accepts, then you're good, and that pair is in halt.
Yes.
Great, wonderful.
Does the machine interpretation help on the understanding of this a little bit, though?
I wasn't completely clear on that.
Oh, okay. That's fine then. Don't worry about it. If you're not clear on it. Right. Good. Because like in my way of writing it here, where you have a machine and input as input,
Mhm.
it's very similar, right? This is telling you what function
Oh, right.
to look at,
Right.
and this is telling you what input to check the function on, the partial function. on.
Right.
That's why they're essentially the same thing. One is talking about will your machine halt? The other is talking about will your function converge?
Oh.
So they are conceptually equivalent in some sense.
Mm-hmm. Right.
Does that make more sense now? Why I equate these two so strongly? This is the one you usually see, actually. This is much more common. Much more common. It's in Sipser, and Sipser is used in all of the basic complexity classes. And so, like whatever Sipser says is the most common, I would say, at this point, just by default.
So why does it, if it halts, then it diverges?
So,
Otherwise it doesn't.
so
What does that mean?
these are not. There's not a perfect translation between these two. Like, I guess I would have to think about how best to translate like machines to functions, but a machine is just a function, right? It's taking inputs and either giving you outputs or not doing it, or just like breaking.
Mhm.
And so if the function gives you an output, that's kind of like the machine giving you an output on some input. So if the function gives you an output on some input, then, but there's certain inputs, because it's partial, there's going to be ones there might be inputs the function is undefined on. And that is conceptually equivalent to your machine never halting and never giving you an answer. Does that make sense? So you can kind of think of like a machine as a partial function, or a partial function as a machine. And then their inputs, like the input to one versus the input to the other. Functions are very general objects. I mean, we get used to thinking about functions on integers. Functions are just are functions defined by relation?
I think they're just sets.
There's
Just sets of tuples. I recall from internal
okay.
theory.
Probably. I mean, there's probably multiple ways of defining functions that are mathematically equivalent.
I actually just asked you a really dumb question.
Oh.
I asked you, why does H bar loop if H halts? Does that make sense? Why that was a stupid question?
Oh, yes.
Because they're just opposites. So.
Well, H bar isn't the opposite.
It's just not.
It's specifically built to not halt when something is when the machine and input halts. Yeah.
Okay.
So you're right. It's
So
opposite. It's the opposite. That's why I call it H bar, is because it's essentially the machine itself is not halting when its input halts on the input, and it's not the inverse. It's not really the inverse of H, right? Because H was just trying to tell you, does it halt or does it not halt? It was trying to halt in all the time. This is kind of like almost like M, the halting of M invert.
Okay, I understand.
Does that make sense?
That makes sense.
Okay, but anyways, I'm gonna do it again. I'm gonna write up his thing because I want to write it up his way. So this is like, I'm gonna say congruent roughly and not really get into that nonsense, and say this is like what he's calling psi of E of N, right? Because this is of M of X by my notation.
How does E halts mean?
E is just the second n.
Give me a sec.
Why
So
are there
get
two
this.
E's? What is that?
He's utilizing the index of the function itself to break it. It's what can you bring up OBS for me? Could you just click the black circle in the bottom? I just want to make sure. I want to mark off when I'm on screen and when I'm off screen, so I don't put stuff off screen. Much obliged. Where's perfect? If you can go back to the other one, that would be awesome. Thank you. Oh, this is actually pretty far. Oh, cool. I have a whole 7 minutes. This will probably be finished outside. But give me 1 sec to write this down. If and 0 see how these are kind of the same, but one is just talking about functions and converging, and the other is talking about machines and halting. That's also why it's called the halting problem. Like, it's not clear why it's called halt when you think of it as functions, in some sense. Like, I don't think it's as obvious, the intuition there, but whatever.
So is the recursion theorem thing that all computable functions can know their own index?
Yes. Well, partial computable functions. Partial is pretty important. Because if they weren't partial, they'd always decide. Let E be given by the recursion theorem such that, okay. Let's define this second thing and take a look at why it's a problem. I guess I can actually write it next to the thing. Okay, let's do it up here. So Okay. Why is this true?
I think it's if and only if not equals.
Right, yeah, sorry. Very good. Definitely. My thing made no sense.
It's true because by definition,
It's by definition.
if that pair was in halt, then it means it doesn't. Then it halts. Yeah.
So let's see.
Converges.
So this is just this, right? So yeah, if this halts, then it's in halt. EE is in halt, right? But what's the problem with that? If this is in halt, then you have what? Right here.
Psi diverges, goes up.
Well, so if EE is in halt, then psi of EE,
Does not halt.
which means this, right? Because this is just psi of EE, does not halt.
Yeah.
Anybody see a problem?
Oh, and that's by the side that we had to find before.
Yeah.
Oh, that actually.
Where's the problem?
It can't halt or it can't diverge because it just
On EE, so by this,
it
it's
converges.
in halt,
Okay, yeah.
but then what does this say?
It's-
It doesn't halt.
It
Like this says it doesn't. This says it converges, right? Thus, it's in halt.
Right.
But then because it's in halt, by this
By the definition of that. Yeah.
psi of the input needs to not converge
How do we know that? How do we
by
know
the
that
definition of psi.
phi sub e of e halts?
So I'm saying assume. I'm assuming
Oh.
that it halts.
If it halts, then
Then EE is in halt
how? Where does that come from?
by definition, because this
Yeah.
is running. E here in the first one is running the function associated with E on n, right? That's what I'm doing here, right? I'm saying psi of E is the function associated with E in the indexing, and I run it on E, which is a valid input, right? And I'm saying it halts. Just
So this
assuming.
only happens because we define psi that way.
That's the point.
Like
Yeah,
we're
you-
just
This, but it's still a counterexample, right? Because it's saying if there existed such a machine, we could build psi. Then psi would be a real. If there existed a machine H that decided the halting problem, we could build psi from it. But when we build psi contradicts itself. There's an input to psi that both converges and diverges,
Right.
How
which
would
makes no
you-
sense.
How would you know if E and N are in halt given that definition of psi?
You don't
You
know
build
if
to
E and N
build
are in
psi.
halt. We just find an E and N that happen to, by this definition, halt and not halt. Like make this machine accept and not accept.
Because
In
like
some sense.
here's what
Sorry.
I'm having trouble understanding is
What's
like, it seems like the definition of psi depends on halt, right?
It does.
But then halt depends on phi, which depends on psi.
No. Whether this machine halts or not depends on this. The definition of halt is fixed in stone, and our ability to decide halt is fixed by our assumption. Because right, we're trying to let's map this out. We're trying to prove that halt is uncomputable, right? So let's assume it is computable.
Mhm.
That gives us a machine H that decides halt.
Okay, so we're assuming
Right?
we have halt for some
Yes.
reason. Okay.
Well, the reason is because we're going to try and find a contradiction from that.
Okay.
If you assume something is true, and then you find that like 1 equals 2, the thing you assume to be true must be false.
Okay.
That's proof by contradiction. So that's the whole method is going to rely on that. So we assume the opposite of what we want to prove, and we're going to find a contradiction, which is what we get in the end. Then we use the machine we get. We use it's not a machine in this case, right? It's a function, right? So we have some function that on any input can tell us if it converges or diverges. For any function and input, it tells you if that function's going to give you an output on that input. Does that make sense?
Okay.
We utilize that function to say, okay, well, let's define psi based on it. We're going to take our assumed the function then and apply it to en, and if it says it's in HALT, we're not going to define psi. Psi is going to diverge. It's going to up arrow, right? And if it converges, we're going to converge with it.
Mm-hmm.
No, sorry.
If it doesn't convert.
Yeah, we're gonna just output 0.
Like we do the opposite, but yeah.
We at least are defined is the whole point. We want to be
Yeah.
defined on it, so we output 0. Okay. So this is just defined. This function is defined based on a function that we've assumed that our assumption implies exists.
Mm-hmm.
So we haven't broken any rules yet. We're just using tools that our assumption has given us. However, when we say, okay, so because of the recursion theorem, something can know its own index. So let's define a function psi that psi sub e that always takes its index as input. Okay? And let's suppose that it converges. Okay? Or another way to put it is that it's essentially, in the machine part, it's a machine that simulates itself. It's a machine that would essentially run the halting problem on its own description.
Mm-hmm.
But here we have a function that it takes its own index as input, and by our definition of this, that's if it converges, then EE is in HALT by the definition of HALT, because something is in HALT if it converges, right? So EE is in HALT now. But if EE is in HALT, then psi of EN diverges on that input, right?
Yes. So how do we get from there to phi diverges?
This equals.
They're equal.
Is it
This
EE?
is phi en.
By EN. Wait.
Equals psi en.
Oh, yeah. Right, of course. I'm an idiot. This is by our definition of this.
Right. And this. Right. And he says this is from the recursion theorem.
This is from the recursion theorem, because it can know its own index.
Right.
So because it can know its own index, we consider all the cases where it's taking itself as input. We consider, yeah. You can start from the other one too, right? You can start from the other side. You could say, assume that phi sub e of e diverges. Well, what does that mean? Then it means it only diverges if it's in HALT, right? But if it's in HALT, then it should converge because it's supposed to halt.
Mm-hmm.
Does that make sense? So like you can go either way, and now you have a contradiction. Everything you've done is a valid, reasonable move, except you made an assumption at one point, so that assumption must be false, and so the whole thing is false. So this proof making sense to you is hopefully mostly sufficient for K.
Because that's how he defines K is the same thing as HALT with just.
I'm gonna get kicked out of here in a second,
Yeah.
so I'm gonna stop here at least for in here, but we can talk a little more about it outside. Sorry, viewers. You won't get to see the ending. You have to give me a minute though to handle the video.